Thank you everyone for being here. We are really excited to be having this tutorial. So the tutorial is going to be in 3 parts, each roughly 30 minutes. I'm going to be talking about an introduction to the interdependent value model. I'll focus on the single item auction setting. I'll talk about what truthfulness is here in this case, and I'll talk about approximation mechanisms, and I will show you one approximately optimal mechanism, definitely. And there's going to be a 15-minute break after that, and then Rebecca and Simon will then tackle more recent works where we look at even more relaxed assumptions in this base model that I introduced. Rebecca will consider what happens when the agents arrive online. So she'll be talking about optimal stopping with interdependent values. And Simo will then talk about the setting where the valuation function is also private. And there will also be a 15-minute break after Rebecca's talk. Okay, so 30 minutes talk each, and with 15 minutes break in the middle between all the talks. That's the rough plan. Okay, so maybe I'll just now go ahead and start with a biased introduction to approximation mechanisms for interdependent valuations. Maybe I should just introduce myself again. I'm Divya Mohan, and I am a postdoctoral fellow at Tel Aviv University. These slides are based on slides thanks to Kiran alone, but all mistakes are mine, definitely. So let's begin. As I said, this is going to be a really biased introduction. One particular reason is that I will only be talking about single item auctions. In fact, for the most of the tutorial, we are going to only focus on single item auctions for the most part. So we have one item for sale. We want to allocate this item, and we have n agents and potential buyers for this item. And our goal for this tutorial is going to be that I want to allocate the item to the bidder with the highest value. Okay, so formally, I can think of this problem like this. I am given as inputs value v1 through vn. I want to output a feasible allocation, basically tell which of the n bidders is going to get the item. And I want to maximize the social welfare. That is, give the item to the bidder at the highest value. This is super easy, just choose the bidder with the highest value, right? But we are, of course, in the EC preview week. Everybody knows that this is not what this is about. The agents are going to have a private value, and moreover, they are going to be strategic. So we need to incentivize them to report truthfully. In particular, we will have truthful payments so that the agents' utilities are maximized when they say truthfully. For concreteness, for the whole of the talk and this whole work, we are going to only look at quasi-linear utilities. Okay, so the agent's value for the given allocation minus the payment is going to be the utility of the agent. This is a very, very fundamental setting, very well understood, and there are very nice classic results. For example, all you have to do is run a second price auction, also known as a victory auction, to achieve the optimal welfare with a truthful mechanism, right? Just allocate the item to the buyer with the highest value, highest reported value, and charge her the second highest value reported. Okay, this is going to be a truthful auction. And since I'm always going to allocate to the highest value bid, I will also get full welfare. Moreover, Meyerson's lemma also tells us that in this nice single item auction setting, to be able to think about truthfulness, all we need to do is to make sure that the allocation is monotone, right? So we can have a truthful auction if the allocation to each agent I is going to be monotonely increasing or non-decreasing in the reported value. And this will ensure truthfulness, and there's a nice unique payment rule that makes sure that we can implement this truthfully. Okay, so we are done. So single item auctions are over. It was done 50 years ago. But a very crucial assumption in this setting, in this very fundamental setting, can be maybe more explained if we look at an example of a second price auction. Let's say I have this house for sale and I want you all to actually participate in an auction, a second price auction for this house. Maybe we won't, I'm not gonna maybe do the whole back and forth for today, but think about how much you will be willing to pay for this house. Okay. But many of you might be wondering, what is this random house? How am I even supposed to know anything about this house to come up with a value? So I'll give you some extra information. This is a 1-bedroom house somewhere in New Jersey. Okay. But there's an additional information with somebody. 500K Kira is bidding. Well, it's in Princeton. So, what do you think now? What is your value? 100K. I don't know. It's 800K. I think you're getting closer because it's a 1-bedroom house. Even though Princeton is kind of cute, it's still in New Jersey. But this was, what if I tell you that this is where Albert Einstein lived during his time in Princeton? Okay. Now what is your value? 4 million? I think actually you're pretty close probably. So 10 years ago, this was sold for 1.5 million roughly. Or like IAS bought it for 1.5 million. So, but it's been 10 years. So I think you probably are correct. Nice. So the whole point of this exercise is that like we don't even know what our value for this item is a priori, especially because our values can depend on the private information that other agents have, right? So we really need to be taking these sort of things into account. And this is so prevalent in many, many settings. For example, you can think of the resale model where when I'm buying something, a house or a painting, I'm not only thinking about how much I like this item, I also need to think about this as a long-term investment, as how much other people like it and what is its potential resale value. And when we buy things online, especially in marketplaces, we don't even have a full information of like what we are getting into, but other bidders who are like more local to the area might have different information. And if we know about this, our values could be well informed. And to study like these sort of settings, we are going to use the interdependent values model to like formally study this. This was introduced by the seminal work of Milgram and Weber in 82, building upon works of Wilson. And they won the 2020 Economics Nobel Prize in part for this work. Again, I'm only going to think about a single item auction with n agents. And each agent I now has a private signal SI, let's say it's between 0 and 1, and a valuation function VI. So this valuation function can potentially depend on all the agent signals, and this is going to map the signals of the agents to the value for the item. Okay, so the agents have private signals and known valuation functions, and you can also think of the valuation functions as being monotone in all agent signals. Maybe for concreteness, you can think about the resale model as follows. An agent I's value for the item is not just about how much they like it, but it's also depends on like a weighted sum of how other agents like it, because this is what they consider as like the potential return in investment. Okay, cool. And in this talk, we are going to look at how can we do nice auction design for the interdependence value model. So the auction design problem is as follows. We are given as input the signals S1 through Sn. Remember, like the instance comes with the valuation functions V1 through Vn. That's given. We want to output a feasible allocation and truthful payments. And again, our objective is to maximize social welfare. Okay. And the utility of the agent is going to be, again, a quasi-linear utility, xi times VI, the allocation XI times their value for the item minus the payment that they need to pay. And by truthfulness, we mean this solution concept. An auction is truthful if the utility of the agent is maximized by reporting her true signal, given that all the other agents are also truthful. Okay, this is the notion of ex post incentive compatibility. Her utility is going to be maximized by reporting the true signal when all the other agents are also reporting true signals. And we are also going to consider individual rationality. That is, the utility is going to be non-negative for every agent when they participate and report truthfully. Okay. Here is a very specific challenge that we face in this setting for truthfulness that does not exist in the more classical mechanism design setting, like the Myersonian setting. Here, an agent's private signal is not only informing us about her own value, but it also really dictates how other agents can value the item. For example, consider that Simo and Rebecca are in an auction to win this painting, but Simo has some information about who has painted this item. He knows whether this was painted by a child, let's say Rebecca's child, or he knows that this was actually painted by Picasso. And depending on what the information is, both Simo's value and Rebecca's value are going to be highly different, right? So here Simo has, who's informed about the item, has a really high incentive to misreport, because if he lies and says that, sorry, I didn't mean to say, how do I put this down? It's fine. Yeah, if Simo has a low, if Simo pretends that it's actually just a painting by a child, Rebecca does not want to win it, and we don't want to give it to Rebecca either. So he has a very high incentive, even though his value, projected value, looks lower, like he still wants to misreport it as a lower signal. Okay, so these are the kinds of things we need to be thinking about in the interdependent values setting. But it turns out there is, again, a very nice characterization in this setting for the single item auctions case, where all we need to ensure is monotonicity in signals. So an allocation can be implemented truthfully in the ex post incentive compatible way, if and only if it is monotone, non-decreasing in the signals of the agents. Okay, and again, we can have like nice uniquely unique payments that makes sure that we can implement this allocation truthfully, and they are like pretty much Meyerson-like payments. But like maybe for like to be super concrete, if you think about a deterministic allocation, that is xi is either 0 or 1, whether I win the item or don't win the item, the payment for this allocation is going to be exactly equal to the value of the agent at their critical signal. So fix everybody else's signal and look at as we increase agent I's signal when they start winning, and at that particular value, that is going to be the payment for this allocation rule. Okay. So maybe like now that we know about truthfulness, maybe we can now figure out a way to obtain the optimal welfare truthfully in this setting. But unfortunately, there's a really strong impossibility results here, even though we have this very nice simple second price auction in the classic setting. Here, if you want to obtain the optimal welfare with a truthful mechanism, this is only possible under a very strong condition on the valuation functions. In particular, it's called the single crossing condition. This is simply because the maximum welfare allocation rule, the allocation rule that maximizes welfare, is going to be a monotone rule if and only if the valuations are single crossing. And a valuation profile is single crossing if for each agent I and j, agent I's value, the influence of agent I's signal on agent I's value is higher than the influence of agent I's signal than on everybody else's value, every other j's value. Okay. So the agent I's sensitivity to her own signal is more compared to other people's sensitivity to her signal. Okay. But when the valuations satisfy single crossing, it turns out we can again have a very simple uh, um, auction that gets the optimal welfare truthfully. The allocation is just a generalized Vickery auction where we give the item to the highest value agent, and now we are going to charge them the critical value that I talked about previously. Okay, and this is going to give us a truthful auction that obtains optimal welfare as long as we have single crossing assumption. Only when we have single crossing assumption. Okay, but what about when we don't have single crossing assumption? For example, the example that we saw before is highly not single crossing because Simo's information influences him a little bit, but it is super more influential on Rebecca's value, right? But this is not just like a made up example that I'm talking about. It's pretty much equivalent to like many other examples that are like well studied in the literature. For example, you can think of as there are two firms competing for like oil drilling rights, and firm one is the one who has the information about how much oil is there in this well that they are trying to bid on. Okay, but firm 2 has a way more better like efficiency in extracting and has much more value per unit of oil that they'll get. So in such scenarios, firm 1 might want to like underreport their findings so that like they have a better shot at winning the value. And this is like a very not single crossing example, which was like well studied in the economics literature. But before like 5 years ago, there has been no guidance on like how to tackle such scenarios because they don't satisfy single crossing, right? Like all the literature before like 2018 has really used this strong notion of single crossing and can only give guarantees when there are like the single crossing like assumptions. And under other when this does not exist, there has been like no way to even guarantee anything. And that's exactly what we are going to be looking about. We are going to figure out how to go beyond this assumption of single crossing, crucially through the lens of approximation. Okay, so let's think about approximating the welfare without single crossing. Unfortunately, there is more bad news here. In the most general case, if I can think of any valuation settings, I cannot really guarantee much if I don't have the single crossing assumption. Let's go back to our favorite example again. Here, actually think of Rebecca as having a really high arbitrary value when she learns that this is a Picasso. Okay, so if the true signal, if it turns out that this painting is actually just made by a child, we should, to get any approximation to the welfare, we should allocate it to Simo, right? Otherwise, Rebecca has 0 value and we will get no approximation guarantee. But in the scenario that it is actually a Picasso, we definitely should allocate to Rebecca if we want any sort of good approximation guarantee, because like her value is just way higher than $200. Okay, but to be truthful, we need to be able to allocate to Simo. If we allocate it to him in the low signal, we should keep allocating to him in the high signal. So no deterministic mechanism here can get any finite approximation guarantee. Okay, and it turns out this is not just for deterministic mechanisms. Even if you allow for randomization in the mechanism without single crossing assumptions, there are still instances where you cannot guarantee better than an n approximation. All you can do is to just assign to a bidder at random. Okay, but we really want to understand what approximations to the social welfare can we guarantee using truthful mechanisms beyond this notion of single crossing. But to be able to do that, we have to make some other reasonable assumptions. We need to restrict ourselves to a good class of valuation functions and try to use the structure in those valuation functions. And in the past, like 5 years or so, there's been a lot of work in the econ-CS community, looking at different classes of valuations beyond single crossing to study whether there are approximately optimal mechanisms here. For example, in EC'18, Eden et al. Considered a more relaxed notion of single crossing, basically using a parameter C to talk about how away from single crossing the setting is, and they give approximation guarantees that depend on this parameter. But in this talk, I'm going to focus more on the these other 2 classes of valuation functions, one submodular over signals, and other is the subadditivity over signals. So under submodular over signals, we know that we can get a constant approximation to the optimal welfare. In particular, the best known constant now is a 3.31. And when you have subadditivity over signals, the best approximation we can guarantee is 4. Okay, and let me define what these 2 classes are before I move on. So evaluation function V is subadditive over signals if for any subset A of the agents, I can look at the value on everybody. If I look at the value of, if I look at the value of V on all the signals, it should be smaller than or equal to the value V on only agents in A, plus the value using the signals only agents not in A. Okay, so if I look at the value on some signal profile, this should be smaller than or equal to the value when I zero out a bunch of agents and keeping only the agents in A, plus the value when I don't zero out the agents not in A, but only zero out the agents in A. That was a double negative, but I hope that was clear. Okay, so this captures scenarios where the signals are not complements, right? Like knowing 2 signals together should not really affect your value way more than knowing them both separately. Okay, cool. And this is a very general class of valuations. And here in particular, a subset of this class has a submodularity property where the marginal increase in the value of a particular signal is going to be much higher if the other signals are lower. Okay, so if I have 2 signal profiles where S minus I is like very, very low compared to S prime minus J coordinate wise is low compared to S prime, then increasing Sj should have a much higher effect in the lower coordinates compared to increasing Sj when the other coordinates are higher. Okay, under these 2 notions, we have good approximation guarantees, and they're like really nice settings that that are like natural, that fall under these notions, right? For example, even if we go back to our Picasso example, if everybody else already has told me that this is a Picasso, and Kira comes and says that, oh, this is not a kid drawing, but it's a Picasso, my change in value is not going to be very high, right? It's going to be maybe it's a bit higher, but it's not going to be that much higher. But if everybody else has only been telling me that this is a kid's drawing, and Kira comes and says, hey, actually, this is a Picasso, then my change in value is going to be way higher. And this is what submodularity is capturing, and also subadditivity is capturing, because the signals are not complements of each other. Okay, cool. So now I'm going to spend the last few minutes talking about a truthful mechanism that does get approximately optimal welfare when we have subadditivity over signals. In particular, it gives a 4 approximation. Let me know if you have any questions before I go to this mechanism. For sub-additivity over signals, do you take expectation over other signals or assume that they are all of lowest value? So far, I have not been telling you anything about priors. Again, this is a biased introduction that only thinks about prior free settings. My signal values are going to be arbitrary. And so for subadditive valuations here, all I'm saying is that this does not have to be the lowest signal. It's just these signals are lower compared to these signals. Okay. Oh, sorry, you asked about subadditivity. Never mind. I'm going to actually look at the lowest signal. Yes. So I will zero out everybody not in A and only look at the signals of A and add it to the value when I zero out the signals in A and have and only look at the signals not in A. There is no expectation. It's going to be the most pessimistic value in these two cases. These are still higher than the value of the when I use all the signals. Cool. Okay. Right. So let's go and see this approximately optimal mechanism. It's called the random sampling Vickrey auction. So in this auction, I'm going to be deciding whether each buyer is going to be a potential winner or a definite loser by tossing a coin with probability half. Okay, I toss a coin. If it lands heads, I tell that they are in set A, who are the potential winners. If it's tails, I say that, oh, they are in set B, they're definitely a loser. So I toss a coin, see that this person's in B. I toss a coin, this person is also in B. Toss a coin, this person is A. And then I do this for everybody. Okay. So I find a random partition of the set of agents and have the potential winners as set A and the definite losers as set B. Okay. And now for each bidder in A, only in A, I'm going to define a proxy value, VI, that uses their own signal SI and the signals of the potential losers, everybody in B, but does not use the signals of the other agents in A. Okay, so the proxy value of I is going to zero out all the signals, all the other signals in A, and only use the signals in B and their own signal SI. And my auction is now very simple. I'm just going to allocate to the an agent in I who has the highest proxy value. Okay. And now let's see whether I can implement this auction truthfully. Is this allocation going to be monotone? Yes, it is monotone, right? For any given partition, look at whether for any given partition, I only look at the agents in A and decide who the highest proxy value agent is. So when they increase their signal, their proxy value increases. So they're only more and more likely to be chosen, right? Agents in B are never going to be chosen. So if they increase, decrease, their allocation is always going to be 0. So that's non-decreasing. But agents in A, their allocation can only increase when they increase their own signal SI. Okay, so yes, we have truthfulness. But is this a good way to allocate choose a winner, right? Like, is using the proxy values a good way to find the right winner? And for this, we are going to use subadditivity crucially and prove this like very, very simple key lemma. So for any agent I who has subadditive valuations, if you partition all the other agents not equal to I uniformly into two sets, A and B, then their proxy value by zeroing out the sets, the signals in A, is going to be at least half their true value in expectation, right? Over the random set choice of sets A and B, if I take the expectation over the random choice of A and B and look at the proxy value of I, that's going to be at least a half approximation, at least going to be half of the true value. And this is simply by like coupling the two events of who gets to be A and who gets to be B. If A equals the set X and B is the complement, and look at the reversed event where A is the complement set X bar and B is X. By subadditivity, I know that my value for the whole set, whole signals S1 through Sn is at most the value of only zeroing out X or X bar, right? So there's immediately, like by coupling these two values, I immediately get that the expected value of the proxy value, 2 times the expected value of the 2 times the expectation of the proxy value is going to be at least my true value. And that gives me my key lemma. And now note that if the highest bidder is in A, which happens with probability half, the winner of the auction who has the highest proxy value also has a value greater than I's proxy value, right? Like, and by the key lemma, we know that any agent I's proxy value is half of the true value. And to be able to get a good approximation to the social welfare, I just need to make sure that my final welfare is somewhere close to the value of the person with the true highest value, I star. And this happens with another probability half. So the winner's value is going to be an expectation given that I star is in A is going to be half of the value of I star, and the probability that I star is actually in A happens with another probability half, and this gives us a 4 approximation. Okay, so the approximation for this random sample Vickery auction is 4 when we have subadditivity over signals. Cool. And with that, I'm actually going to wrap up. I hope I gave a sense of like why approximations are interesting and important when we have interdependent values model in the single item auction setting. And this has been studied a lot in like in other areas from like combinatorial auctions and like looking at revenue maximization, looking at public project settings or like fair division. And there's like some of these are like super recent works from the past like 5 years. So if you're interested, like check that out. But next we are going to see from Rebecca and Simo, how can we like relax the assumptions that I am making in this base model of interdependent values, and can we still get approximation guarantees in this? With that, I'll wrap up. Thank you so much for listening.